Have you ever been on a plane, looked out the window at that massive engine, and just wondered, how on earth does that thing work? I mean, these are machines that operate on the absolute ragged edge of what's possible, day in and day out. So how do they survive conditions that should, by all rights, just tear them apart? Well, that's what we're going to find out. So let's start with a really simple, kind of brutal question. What happens when this piece of machinery, this multi-million-dollar marvel of engineering, smacks into a bird at hundreds of miles an hour? It sounds like a strange thought experiment, but for pilots and engineers, it is a constant, deadly serious reality. And if you need a reminder of just how serious it is, you just have to think back to the miracle on the Hudson. You know the story. Captain Sullenberger landed an Airbus A320 on a river, saving everyone on board. And what caused it? A flock of birds that took out both engines at once. It's the perfect and, frankly, terrifying example of what's at stake.
And here's the thing, this isn't some one-in-a-million freak accident. We're talking more than 10,000 bird strikes every single year, and that's just in the United States. That breaks down to over 26 times a day. So for engineers, it's not a question of if an engine will hit a bird, it's a guarantee that it will, and it has to be ready. So how in the world do you build a machine to withstand that kind of random, violent chaos? Well, the answer is you have to get even more violent and chaotic in your testing. You basically have to put these engines through the worst day of their lives again and again, long before they ever get bolted to a wing.
Which leads us to the, let's call it the infamous chicken gun. And yeah, it is exactly what it sounds like. Engineers use a giant compressed air cannon to launch bird carcasses directly into a running engine. It's pretty gruesome, I know, but the goal is to prove that the engine can suck in a bird, maybe lose some power, but not explode and send shrapnel flying through the plane. It's a vital, if not very pretty, test.
Okay, so it can handle a bird, but what about weather? Like the worst rainstorm you could possibly imagine. To test for that, they just unleash a fire hose of biblical proportions on it. We're talking up to 900 gallons of water a minute. The engine has to swallow all of it, keep the fire lit inside, and just power right through without flaming out.
And of course, it's not just liquid water they have to worry about. They do the exact same thing with massive, hard-packed balls of ice to simulate a severe hailstorm. You've got these fan blades spinning at supersonic speeds, and they have to be able to just, well, chew up solid ice and spit it out the back without shattering into a million pieces. But this is the one. This is the nightmare scenario. It's one thing to test for threats from the outside, but what if the engine fails from the inside? For the blade-off test, they literally strap a small explosive to one of the fan blades and blow it off while the engine is at full throttle. The goal isn't to see if the engine survives. It won't. The goal is to see if the engine's casing, the containment ring, can catch that blade, which is now a piece of shrapnel with enough energy to slice through the plane's cabin. It absolutely has to be contained. Okay, so birds, torrential rain, hail, even its own internal explosions. These engines are built to take an unbelievable amount of punishment. So what kind of machine can do all that? How can something be so incredibly complex and yet so ridiculously tough? Well, for one, they are staggeringly expensive. A single top-of-the-line engine for a plane like the Airbus A380 can set you back $35 million. I mean, think about that. For the price of just one of these, you could buy a whole garage full of Lamborghinis. And they're not just expensive. They are a huge part of the aircraft itself. In fact, on many planes, the engines can make up almost half of the aircraft's entire weight. They are these massive, dense, incredibly powerful hearts of the machine. So that toughness we've been talking about, it comes from this fanatical, almost obsessive focus on precision every step of the way. You know, from the very beginning with advanced computer models to selecting these space-age materials to manufacturing parts with microscopic accuracy and then having skilled technicians assemble thousands of pieces by hand. Everything is checked and double-checked before it even gets to those brutal tests we saw. But the real secret, the thing that truly allows these engines to do the impossible, it's not just in the big picture design. It's hidden way, way down, deep inside the metals themselves. To really understand it, we have to shrink ourselves down from the size of an engine to the size of an atom. And that's where we meet the hero of our story, nickel-based superalloys. So you start with nickel as your main ingredient, but then you add this very specific cocktail of other elements. Each one has a job. One might add strength, another adds heat resistance, another fights off corrosion. It's like baking the world's most extreme cake. Here, check this out. This is an actual recipe for a specific superalloy. You can see things in there like tungsten and rhenium. These are incredibly dense, tough elements that have insanely high melting points. They're added in these very precise percentages. So you see, this isn't just a hunk of metal. It's a material that has been chemically designed to have almost supernatural powers. But believe it or not, even that recipe isn't the whole story. To find the true source of its incredible strength, we've got to go deeper. We need to zoom in past what any normal microscope can see. We're going to look at the internal architecture of the metal itself. And this is the magic. This image right here reveals the secret. What you're seeing isn't just a solid, uniform chunk of metal. It's this perfectly ordered two-part crystal structure. It looks like a tiny, intricate labyrinth. And for scale, that little bar at the bottom is just 2 micrometers. That's about 50 times smaller than the width of one of your hairs. Now, the best way to think about this structure is to imagine reinforced concrete. You've got 2 parts working together. First, there's the gamma phase, which is like the concrete itself. It's the strong but kind of flexible foundation. But embedded all throughout it are these little cubic gamma prime precipitates, and those act like microscopic steel rebar, creating this incredibly strong internal grid that physically blocks tiny fractures from ever spreading. So what does all this atomic-level engineering actually create? It creates this. This is a single turbine blade. This one part lives its entire life inside a raging inferno, spinning thousands of times a minute at temperatures that would instantly melt steel. Its very existence is just a miracle of material science. And the only reason it can survive is because of this. The incredible strength of that blade you can hold in your hand is a direct result of this invisible, nanoscale architecture inside of it. Every single one of those little cubes is doing its job, stopping a tiny crack from becoming a catastrophic failure. So here it is, the big takeaway. The reason that engine can swallow a bird or digest a hailstorm or even survive its own parts exploding is because deep within its most critical components, there is this invisible, man-made labyrinth designed to stop a crack before it can even get started. It's engineered failure-proofing at the atomic level. I mean, it is just an absolutely incredible fusion of engineering and pure science, and it's what allows us to fly safely all over the world. It really makes you wonder, if we can already design metals, atom by atom, to survive inside a jet engine, what other so-called impossible materials are we about to create? And how are they going to completely change our world next?